The gear that comprises the second idler is a little bit different than the rest of the gears inside the gearbox. The other gears are all 1/4 inch thick, but the second idler has to engage 2 of these gears at the same time, so it's actually twice as thick. And I'm going to try something a little bit different in making it. I could have done something like double these gears up or make one extra thick one, but I decided what I was going to try and do instead was to make the gear and the shaft all out of one piece. If I do that, I eliminate the necessity to cut woodruff keys in the shaft, and I eliminate the potential of having something slip between the gear and the shaft. So I've machined this piece of aluminum that I have down to 1.625, which is the outside diameter of the gears, and then I'm going to mount this in the 4th axis of the milling machine and actually mill the teeth into this first, and then I'm going to come back and cut away the rest of the aluminum that will comprise the shaft, and hopefully we're going to end up with one solid piece that consists of the shaft and the gear. This is probably a good time to review just exactly where inside this gearbox the second idler is. This is a view of the gearbox, an isometric view of the gearbox, where this is the main housing body here, and then this is the input side down here, and these are the output shafts. In this view, you can see some of the hidden lines inside the gearbox. What I'm going to do at this point is add the idlers so that you can see where they are. That's the second idler, and here are the first idlers and their gears and their shafts, and the main gears, the inner and outer main gears, are on the shaft. I think the only one we're not showing here is the outer main gear, which is that one right there. But what we're talking about right now with this particular piece of the gearbox is the construction of the second idler and its shaft made integrally as one piece. Now we can go ahead and get rid of all of the other parts of the gearbox that are not pertinent to what we're doing today. And that's what we have. That consists of the gear and the shafts, and that's what we're going to try and produce out of this one piece of aluminum. I'm now set up with the 4th axis on the milling machine, and I have placed a gear cutter in the spindle of the mill. This gear cutter is a 16 diametral pitch gear cutter intended to cut between 21 and 24 teeth, so that makes it the number 5 cutter, and it will cut each tooth successively, and the 4th axis will rotate between teeth, and eventually we'll cut all the way around this piece of aluminum stock here. I've got a couple more adjustments that I have to complete before I cut the first gear tooth, which is going to be back here on this back side, and then with that we can get going. Alright, it's taken me a couple minutes to make some changes to my NC program to accommodate the slightly different way that I'm working on these gears. But I believe I've got that done, and I'm about ready to launch the process here and get on to cutting these gears. So I'm going to go ahead and remove that single block restriction, and we'll see how we do. Cutter set up to make two cuts. The first one is 131 thousandths deep, and the second cut is down to full depth, which is 141 thousandths deep. Now, in case you're wondering where that number for the hole depth came from, I will show you. This is Machinery's Handbook, and I am fortunate enough to own a 30th edition, and it contains almost all the information one would ever want when messing around with this kind of machinery. I'm going to refer to the section in this book on gears, and they have given us a very convenient drawing on page 2145 that we can zoom in on a little bit, and that will permit us to see what some of these various terms really mean. If you note here on this picture, there's a picture of the gear tooth, and the gear tooth is bisected by this circle, which is called the pitch circle. And then there are two values for the distance from the top of the gear tooth to the pitch circle, and then from the pitch circle down to the very bottom of the tooth, which is called the hole depth. What we're interested in is the distance between the top of the tooth and the bottom of the tooth, which is the hole depth, and that's equal to the sum of the addendum plus the dedendum, as you can see here in this picture. Now, the Machinery's Handbook has also given us a convenient table for the dimensions of standard gear tooth parts, and it lists the standard addendum depth and dedendum depth for a variety of gears based upon their diametral pitch. And if we roll down here to a diametral pitch of 16, we can see that the addendum is 0.0625 and the dedendum is 0.0781. And if we remember from before, the hole depth is the sum of those two numbers, and if we add them together, we're going to get 0.1406, which I have rounded up to 0.141. I think it's a little bit easier to see this process going on from back here. Right now we've got about 3 teeth cut. This will give you an idea of what the NC program looks like as it proceeds along with this gear cutting. You can see in the upper right corner the graphic there shows you where the tool is in accordance with the code that is on the left side of the screen. Now it's up to the machinist to make sure that the actual physical location of the parts of the machine are where the NC code thinks it is. Okay, we're done. We've run through this sequence, and here's the gear teeth. And here's my mating gear. So we can, looks like it works pretty good. You know, they mate. Alrighty then, I've checked this thing up in a lathe, and we're going to see if I can get this thing in focus. We're going to progressively hack away at it until everything that doesn't look like a shaft with a gear on it is gone. And then hopefully we're going to have what we want at the end. It's a little hard to take video of the action going on inside this lathe because it's in a cabinet, and the door has to be closed in order for it to work. But I'll do what I can. That howling noise is the tool cutting away at the gear teeth. I'm going to step this down in stages because it gives me something substantial to hang on to. Well, it's getting there. It's slowly coming down. This is the long end of the shaft, that being the short end. And I'm now placing the bearing seats on this side. As soon as I get that done, I have to bring this to the final diameter, which is just it's a half a thousandths bigger than a quarter. So it's, 0.2505. We'll do that next. Okay, I need an interference fit on the end of this this bearing. And it's supposed to be 2505. And we ended up with, you can see that 2504. Not bad. That's within 1/10,000th of what we were looking for. I like this machine. Well, here it is. I'm not entirely happy with it. There's some spots where It left a little bit of burr that's kind of hard to get off, but fundamentally that's what we wanted, was the thicker gear that will be able to run two of these gears at different elevations, and on the shaft that fits in the housing. So it runs, this is the second idler, so the second idler runs up in here, like that. And we'll see how it works. I'm including some photographs that I've taken of a few of the other parts, including the first idler gears and shaft. You'll notice that the shaft here has a set of slots with some keys installed. Those are Woodruff keys that I cut into the aluminum shaft. I'm also including some photographs of the housing body and the lower, or that is the outer shaft bearing supporter, which is the main structural supporter for the outer shaft, and it carries the thrust loads of the outer shaft propeller that are transmitted into the gearbox. Next time I'm going to work on the inner and outer drive shafts themselves. They're made of steel, and they're going to require a couple of different techniques that I've used previously. See you then.